So today on campus we did some enrichment where the students were given these problems and everybody worked on them, and then we're going to go over them now. So if you're watching this as an online student, you can try these problems for yourself. Pause the video and then resume when you're ready to continue. You can also download this file from the course website. So here are the first two problems asking you to name the molecule and then name these two. And we're going to write reactions showing reductions. So try these. That says name the products, and I think everybody in here is capable of doing that. But on a later one where we get to, we have some carboxylic acids. We technically haven't talked about those yet. So carboxylic acids are not considered the topic for this assignment. There's number 3, what will happen when these are mixed with Benedict's reagent. And then write the reaction between pentanal and 1-butanol. What type of reaction is this? Here's the one where I said name the product. You're going to be getting a carboxylic acid, which we technically haven't talked about yet, but that can just be a skills test for you there. Number 6, here's the reaction between 2-pentanone and 1-butanol, type of reaction. And then number 7, rank in order of increasing boiling point. So again, pause the video, try it for yourself. When you're ready to see the answers, hit resume. You can also just download the entire PDF from the course website, try the whole thing, and then watch this video when you're ready. So now we're going to go over these today. So let's do some naming. So when we're dealing with molecules like this, where is carbon number 1? Right, the carbonyl carbon's number 1, and then are we going to number clockwise or counterclockwise? Clockwise, right? So 1, 2, 3, 4, 5, 6, 7, 8. So this would be what? 3-chloro, 5-methyl, cyclooctanone, right? Cyclooct and -one. And there is a back-to-back OO. I know that feels kind of weird writing, but it is cyclooctanone. All right. Feeling good on number 1? Let's look at number 2. I should say part B. Where's carbon number 1? On the left, on the right, top, bottom, where? It has to be this one. Why?
Because it gives you suspicion of small numbers.
Gives us suspicion of smaller numbers, but there's another reason too. The aldehyde carbon is always number 1, right? All right, so we've got, what kind of group do we have on 2 and 5? And then what's this? So what comes first? The ethyl groups, so it would be what? 2,5-diethyl, 3-methyl, heptanal, right? Hept and al, right? Aldehyde ends in al. You don't need the 1, right? Because the aldehyde carbon is number 1 when it's linear. All right, in part C, the aldehyde is obviously going to be number 1, but there are 2 aldehydes. So you have to pick which one's number 1. The left or the right? The left, right. So this is 1, 2, 3, 4, 5, right? So this would be 2-methyl. What is it called when there are 2 aldehydes? A dial, right? So this is 2-methyl pentadiol. Pentadiol.
Oh, I missed one. I missed this one. I thought it was butadiol.
Oh, yep, that's a carbon. So So that still counts as part of the chain. Yep. I think some textbooks may also write it as 2-methyl pentane dial. You may see that in some textbooks as well. But I'm pretty sure that's the way your book presents it. Pentane dial, penta dial. I'm pretty sure some textbooks may even show that convention. But both would be acceptable. All right, so there was part B and part C. Let's look at part D. So, does it matter which one's carbon number 1? No, so long as you number so that they both have the lowest numbers possible, right? So if you pick this one, you need a number counterclockwise. And if you pick this as one, you need a number clockwise. So it really doesn't matter which one you pick, so long as you number appropriately. Now, there are no substituents to worry about. But let's just pretend if we had a chloro right there, right, you put that substituent first. Now, do we have to say 1, 3 in here? We do, right? Because we could have the ketones on 1 and 2, or we could have a ketone on 1 and 4, right? Because this is in a ring and they're ketones. Anytime you've got ketones, you have to designate the numbers, right? Aldehydes, you never have to designate numbers because they're always on ends. But with ketones, you always have to designate numbers. So this would be 1, 3, cyclohepta, what? Dione, right? Oh, hep. I said hep. It's not 7-membered ring. It's a hexa. Hexadione. I don't know what I was thinking. Hexa. That's a 6-membered ring, not a 7-membered ring. All right, so with ketones, you always have to state numbers. Aldehydes, you never have to state numbers because they are number 1 by default. Could you have an aldehyde in a ring like this?
Yes.
If it was coming off, right? If it was coming off. But it couldn't actually be one of the carbons of the ring. All right. Let's do some reduction. So reduction is a reaction with what? H2, right? And what catalyst do we need? Platinum would work, palladium would work, right? We increase the temperature. So what's going to happen to this functional group? It becomes an alcohol, right? So our molecule with the bromine stays intact. This just becomes an OH now, right? And it says to name the product. So what would the name of this be? Cyclopentanol. And just for practice, what would the name of this have been? Right. The ketone becomes an alcohol. Right, so 2 letters change, essentially, out of all that. Well, 3 letters. Okay, when this is reduced, you can write platinum, palladium, whichever makes you happy, increase the temperature. What's going to happen? Does any of this part change? No, right? So this is 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. What's on carbon number 1 now? An alcohol, right? And then carbon number 1, 2, 3, 4, 5, 6. So what's the name of this?
3,5,5 trimethyl or trimethyl.
Yep, 3,5,5-trimethyl.
Octanol.
Don't forget the 1, right? Because an alcohol can be anywhere. So you need the 1. 1 octanol. Right? Aldehyde, you don't need that number 1 because that's by default number 1. But an alcohol can be anywhere. So you do need that 1 back as part of the name. Just for practice, how about we name this? Obviously, we're naming from the right. So this is still 3,5,5-trimethyl. But what is the rest of it? Octanol. Right? Aldehyde becoming an alcohol. Do you feel good about this one? All right. Let's look at number 3. What will happen when each of the following is mixed with Benedict's reagent? What we see, what will be formed? Okay. So 2-chloropentanal. 1, 2, 3, 4, 5. 2-chloro. And we're adding this to Benedict's reagent. Benedict's reagent contains Cu2 plus, becoming Cu plus, right? Does that do anything here? The color change would occur, yeah. What's going to happen here? So this is the reduction. What's going to happen to this molecule? If this part's the reduction, this part gets oxidized. Can you oxidize an aldehyde? Yes, again, because that hydrogen is what becomes oxidized. You oxidize that aldehyde into a carboxylic acid. 1, 2, 3, 4, 5. So what happens? The aldehyde is oxidized to a carboxylic acid, which you don't know how to name yet. That's okay. The Cu2 plus is reduced to Cu plus, which precipitates out. And then what will you see? What would you physically see?
The color change.
Color change from what?
Blue to red.
Right. You would physically observe a color change. This is the chemistry of what happens, right? This is what you would see. All right, 2-butanone. 1, 2, 3, 4, butanone. We try to combine this. This requires speed as well. What are we going to get?
It oxidizes.
Can you oxidize a ketone?
No.
Nope, no reaction. Right? You can't oxidize a ketone. So what would you see? Color stays blue, right? Because copper 2 is blue. So this is not going to happen, right? No reaction. This reduction won't occur because there's no oxidation that's taking place. That's why the color remains blue. Right, so there's no reduction because there's no oxidation. Cyclohexanone. So there's our 6-membered ring. Hexanone. If we add Cu2 plus to this, is it going to oxidize? And we increase the temperature as much as we want, right? Again, no reaction. So you're not going to get this. There's no reduction because there's no oxidation, right? Oxidation and reduction occur together. This can't happen because this part can't happen. And this is the exact same observation. Colored stay blue, right? And then benzaldehyde, that's a benzene ring. We add copper 2 to this. We heat it. Will this reaction occur? Yes, because this is going to get, this is the reduction. What's the oxidation going to look like? Not an alcohol. The reduction is going on here. It would be an oxidation. When you oxidize an aldehyde, what do you get? You get a carboxylic acid. So you get benzoic acid. So the aldehyde, again, is oxidized to a carboxylic acid. And copper 2 is reduced to copper 1, which comes out as a precipitate. Right, so what do you see? You see a change in color from blue to red. It's a reddish brown. Right, you see that precipitate come right out. So when you oxidize an aldehyde, you get a carboxylic acid, right? When you reduce it, like in the previous problem, using hydrogenation, that's when you get an alcohol. So aldehydes and ketones can both be reduced, but only one can be oxidized, right? Because there's no hydrogen to oxidize here. If you had a OH sticking out here, 1, 2, 3, 4, 5, that's just not possible. But here, this hydrogen sticking out, that's what's getting oxidized to a carboxylic acid. Do you see the difference between oxidizing an aldehyde and reducing? Right? Aldehydes and ketones can both be reduced, but only aldehydes can be oxidized. And when you oxidize, you get a carboxylic acid every time.
So when you reduce it, that's when you get the alcohol?
Yes, when you reduce it, that's when you get your alcohol back. And that's hydrogenation, right? Reaction with H2. Just like we did with alkenes and alkynes. Does that make sense? All right. All right, let's go look at number 4. Right, the reaction that occurs between pentanal and 1-butanol. What type of reaction is this? No. Let's do the reaction first. Pentanal looks like this. 1, 2, 3, 4, 5. Right? And butanol looks like this. Remember, I wrote it backwards. 1, 2, 3, 4. This is a 2-step process, right? In step 1, we form the intermediate. You remember now? So you have to identify the positive parts and the negative parts. In the aldehyde, which one's the negative part? The oxygen or the carbon? The oxygen is the negative part, and the positive part is the carbon of the carbonyl, right? And then in the alcohol, which part's the positive part? The hydrogen, and where's the negative part? Right. So think about little positives and negatives, right? The positive goes to the negative, and the negative goes to the positive. So we get our intermediate. So we redraw this exactly as it is. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. But now this O has what on it? An H, and that double bond's gone, right? OH. And then this carbon has a bond to this O, and then this just drags along with it, right? So this is 1, 2, 3, 4. 1, 2, 3, 4. And then we put brackets around it to show that it's an intermediate. Do we remember this now?
Yeah.
Right, this is called addition. Now, that's step one, right? What happens in step two? You take your intermediate, right? So we're just going to redraw it as is. 1, 2, 3, 4, 5. O, 1, 2, 3, 4. OH. Right? Your intermediate is going to react with another aldehyde or another alcohol molecule. Which one?
The alcohol.
It reacts with the alcohol, right? And what happens? The OH is displaced as H2O, right? And you get a second ether, right? This and this get together and make water. So you get water as your other product. So this gets redrawn on the top the same. 1, 2, 3, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then O. And then 1, 2, 3, 4. That part hasn't changed, right? 1, 2, 3, 4. And then where this was is where your second ether is. O. 1, 2, 3, 4. And then your other product is H2O. Right? So this final product has 2 ethers in it. I wouldn't ask you to name it, but do you think you could figure it out? What kind of group is this? 1, 2, 3, 4. It's a butoxy, right? And then this is also a butoxy. And then this is a 1, 2, 3, 4, 5. Right? So this is a pentane. So this would be 1,1 dibutoxy pentane. I wouldn't ask you to name that on a test, but I just like going through it so you can get the practice. All right, I wouldn't ask you to name that on a test. I would ask you to draw a product, though. Do you understand how we got this product? It's a 2-step process, right? In step 1, you get that intermediate, and then in step 2, your intermediate reacts with the second alcohol molecule. You have as many of these in there as you want, right? Because this is just a solution containing as many as you want, right? You're going to have more than 2 floating around in there. So you get a product that has 2 ethers and then water. I wouldn't ask you to name it, but just for fun, just for the intellectual challenge, right? That would be the IUPAC name for that. Make sense? And this is called an addition, right? It's an aldehyde addition. Aldehyde plus alcohol is called an addition. All right. Which of the following can be oxidized? This is basically asking the same thing as what will happen when reacting with Benedict's reagent, right? You're either figuring out can it be oxidized or not. So let's just go through and identify first the ones that cannot be oxidized. Ketone, can that one be oxidized? No, why not?
Only the aldehydes can be.
Right, you can't oxidize a ketone. There's no hydrogen to oxidize. Aldehyde, can this one be oxidized? Yes. All right, when you oxidize this, remember aldehydes are readily oxidized. They oxidize pretty easily. That's one of the reasons why you have to make it fresh if you want to use it, because it'll oxidize just sitting on your shelf. So this is HEP. 1, 2, 3, 4, 5, 6. I hate where that scene is located. Seriously, in the most inconvenient spot. 1, 2, 3, 4, 5, 6, 7. That's really number 1. 1, 2, 3, bromo. 4,4-dimethyl, because it says, show the reaction. I didn't tell you what the oxidizing agent is. So what do you do if you're not told what the oxidizer is? O in brackets. Right, so what happens to this functional group? No, you just reduced it. When you oxidize it, the H that's right here becomes OH, right? And then this bromine and those methyl groups don't change. Now it says name the products. We don't know how to name carboxylic acids yet, but it's not hard, right? This would just be 3-bromo-4,4-dimethyl heptanoic acid. We're naming carboxylic acids when we come back from spring break. Can we oxidize this? Nope. Why not? Can't oxidize ketones. There's not a hydrogen available to be oxidized. How do we feel on number 5? All right. Number 6 is another addition reaction, but this time we're using a ketone and an alcohol, which is fine. You can do an addition. This is a ketone addition. So this is a 2-step process. Right, we're using the same alcohol. So in step 1, we're still going to form our intermediate, but this time we're starting with a ketone. 1, 2, 3, 4, 5, 2-pentanone, and 1-butanol. Okay, let's identify the positive parts and the negative parts. On the carbonyl, where's the positive part? The carbon, and this is the negative, right? And then where's the positive part here? The hydrogen, and the negative is on the oxygen, right? So this goes here, this whole piece goes here, so this gives us our intermediate. So this chain hasn't changed, right? 1, 2, 3, 4, 5. And now what's this O? It's an OH, right? And then what's coming off of this carbon? All of this, right? O, and then 1, 2, 3, 4. 1, 2, 3, 4, right? And we put brackets around it to show that it's an intermediate. That's not our final product, right? That's why we put the brackets around it. And now in step 2, we're going to redraw our intermediate. So 1, 2, 3, 4, 5, OH, O, 1, 2, 3, 4. This is going to react with a second alcohol or ketone. It's going to take another one of these alcohols. And what's going to happen? OH and H make water, right? That's displaced. And final product has 2 ethers. Now again, we're not getting into the nitty-gritties of how this happens. We're just looking at the big picture, right? When you take full organic, you'll draw the full mechanisms with your electrons being pushed around and all that fun stuff. But here in elementary organic, we don't go into that level of depth. We're just looking at the big picture. So we're still drawing this backbone the same. 1, 2, 3, 4, 5. Now we've got O. 1, 2, 3, 4. And then O. 1, 2, 3, 4. Right, our other product is H2O. Now I wouldn't ask you to name this on a test, but do you think you could? This is a butoxy, right? This is a butoxy. Where is it now? Is it on carbon 1? It's on carbon 2, right? So it'd be 2,2-dibutoxy. And then this is a 5-carbon chain, right? Pentane. Again, I wouldn't ask you to do that on test, but just for the intellectual stimulation. Makes sense? And then number 7 is extremely easy by comparison, right? Because all we're doing in number 7 is ranking some boiling points. Rank in order of increasing boiling point, explain your reasoning. All right, let's draw all these molecules out. So diethyl ether has 1, 2, and then O, and then 1, 2, right? Hexane is just a 6-member chain, 1, 2, 3, 4, 5, 6. 1 hexanol, 1, 2, 3, 4, 5, 6. OH, and then 2 hexanol, 1, 2, 3, 4, 5, 6. All right, let's go through and list our IMFs, because that's the only way we can do this, right? What kind of IMFs does diethyl ether have? It has weak dipole-dipole, right? That's the strongest IMF, plus London, right? What does hexane have? London only, right? What does 1 hexanol have? Right, H bonding and London, right? And then 2 hexanone has what? Dipole-dipole. Plus London. So now we're putting these in order of increasing boiling point. So that means which one goes first? The lowest boiling point, right. So that means hexane is less than what? Who's next? Diethyl ether. Which is less than 2 hexanone. Which is less than 1 hexanol. Right? And then the reasoning would be increase IMFs equals increase boiling point, because increase energy required to vaporize. Right? Are you actually breaking bonds when you boil something? No, okay? When you vaporize something, you're not breaking bonds. So don't say something like, this requires more energy to break bonds. Because we're not talking about the bond energy. We're talking about, this is a stronger magnet, right, than this is. IMFs can be thought of like magnets. You're not breaking bonds. Don't use the word bond breakage ever when we're explaining a boiling point, right? Because you're not breaking bonds. You are just think of it as magnets, right? These are much stronger magnets or much stronger pieces of Velcro to pull apart than these are. Make sense? Any questions? All right, so that's where we're going to stop.